As an introduction, we have looked at some systems that show some principles with phase diagrams. We are now going to look at real phase diagrams with the real elements. And the first system we're going to look at is a copper-nickel system. It's a so-called two-component system, of course, and the simplicity with that system is that there is total solubility both in the liquid and in the solid. There are a number of systems like that, but this is an example, and this is the simplest type of phase diagram. Here we see the phase diagram for copper and nickel. We see that this axis corresponds to 100% copper, and this axis corresponds to 100% nickel. That is pure copper and pure nickel. We can read on this axis the melting point of copper, which is 10,085 degrees centigrade. And above that temperature is liquid, and below it's solid. For nickel we can do the same, read the melting point here, and here is the liquid, and here is the solid. Then in between we see the phase diagram. Here we have liquid with total solubility here in temperatures above the nickel melting point. And here we have total solubility in the solid also. But in between here we see two lines that gives us an area. That is a two-phase region. And in that two-phase region both liquid and solid will exist. All the time when we have compositions and temperature combinations that we end up in this region, we will have both phases, both liquid and solid. We can also recognize this line as a solubility line, as we discussed before. It shows in principle the solubility of, down here it shows the solubility of nickel into liquid copper melt. We can also see the Solaris line here. And it can be regarded as a line where the material starts to melt. I mean, for all these compositions we can read here when the melt starts, when we increase the temperature. When we come up to the solids, we start getting some melting. And now we're going to focus on a certain area here. We will focus on this point, B, which is at 1250 degrees centigrade and as a composition of 35% nickel. Here we see a magnified picture of the two-phase region. That is the region here between the liquidus and the Solaris line. And as we said before, between here we will have two phases, namely liquid and solid. And we focus on this point B, as we said before. It's at 1250 degrees and at a composition of 35% nickel into copper. And we can draw a line here. Such a line is called a tie line. That's the temperature now that we are working on. And at this line we can make a judgment of the amount of solid respective liquid we have. But if you assume that we start moving along this line, I mean, if we move away to the left, close to the liquidus, we get more and more liquid. And when we are exactly on the liquidus line, we will have 100% liquid. If we do the opposite, go to the right, we will get 100% solid at this position. So we can therefore judge from the lengths of these two parts of the tie line how much solid respective liquid we actually have. In this case we see that this part we are closer to the liquid side, so we'll have more liquid than solid. Roughly we can say that this part of the line is about 30% of the total length. When we are close to the liquid side, it means that we have about 30% solid and we have about 70% liquid. And it's important to remember here that when we're approaching this line, we get more and more liquid, although this part of the tie line is shorter, but it means that the amount of liquid is going to increase. We can also read the compositions here in the respective phases. We see here, and all the time when we are working at this temperature, that the liquid composition is going to be here, which means it's about 32%. And all the time the solid, that is the solid phase compositions are going to be here, which is about 43% nickel. So that's the way we can use the phase diagram. And now we'll continue to do some simple calculations on this tie line and see that we actually can calculate or learn a method to calculate exactly the fractions of the two phases. Here we have another phase diagram, but it is of the similar type as the one we have just looked at. The difference is that now the element on this side has a higher melting point than the element on that side. It means that this feature in the center of the diagram has another direction, but that makes no difference. This is a schematic diagram. And now we're going to work at the temperature of 400 degrees, that means this line, and then we get the tie line here. And then we assume that we have 60% of that element, so we get a line also here, so we are lying in that point. And when we are in this point, we know that we are in a two-phase field. We have solid and we have liquid. And now we're going to judge how much liquid do we have when we have this temperature and this composition. Well, one simple way of doing this, if you have the diagram on the paper, you can draw a scale. Down here I have drawn a scale from that point to that point. And we know that in this point we have 0 liquid phase, and in that point we have 100% liquid phase. And this is a linear scale. So now we can just see here on the scale, where are we? Well, we can judge that it's maybe about 30 to 40% liquid when we are in this point. And many times that actually is enough to make a rough judgment. But now we can continue and do a more careful calculation of this. We will use the distances on each side of this balancing point, that distance and that distance, and we will call them A and B. And if you want to assign here the weight percent liquid, that will be equal to A over A plus B. Now we have to find what A and B is, and that we can get directly from the phase diagram. So A, that equal to that distance. It means that that's 60 minus 43, or roughly, no, it's 48, we see, and that will be 12, and then A plus B. Of course we can also find B, but now if we're going to use A plus B, we only take the whole distance, A plus B, that's this distance. And that means that we go from 82 minus the value here, that is also 48, which means that is 34. So A is 12 and A plus B is 34. So now we can add that here. 12 divided by 34. And that will be that will be 0.35. And that's the fraction liquid we have. It means that we have 35% liquid at this point in this two-phase field. And in this point, that is at average composition of 60% and at the temperature 400 degrees. We now have calculated that we have 35% liquid and that's 65% solid. You can now do the same yourself in the copper-nickel system. That is, you can calculate the fraction liquid at the point we focused on. You can go back to the copper-nickel system on the focused part of the diagram, and that is at 1250 degrees and a composition of 35% nickel. And use the lever rule to calculate the fraction liquid. You can also see the answer and solution in the paper if you read on in the text.